Hi, and welcome back to the Low Level Devil channel's Raspberry Pi Bare Metal series. In the previous video, we covered how to use DMA with video output. I know it's been a while since I've done any videos in this series. I've kind of been stuck on where to go. I do plan to eventually add some support for disk access, which kind of led me down a road where I ran into issues with unaligned data structures, which through some research I found that ARM doesn't support without the MMU being enabled. So in this video I'm going to cover enabling the MMU. So let's get started. I'm going to start by showing you a simple example of this align issue. So let's start by having a data structure called align check 1. So let's see, this align check has several different variables. We have a U8A, B, and C, so that's 3 U8s, and then a U32D. So you would now, let's say you have a buffer that you want to read and load into this structure. So I'll just create a little buffer here. We'll have it 0x10, 20, 30, 40, 50, 60, and 70. So if we loaded this into this data structure, the value A would be filled with 10, B with 20, C with 30, and D should be 40, 50, 60, 70, but in reverse order, of course. So what happens if we actually try to do this? So let's just print out some data here. Align check. So I'm going to create an instance of this check, AC1. So now I'm going to just mem copy that data structure. It's 7 bytes. So now I'm going to printf each of the values from there. So we'll have A, B, C, and D. We'll just print out the hex values of those. So again, A should be 10, and then 20, 30, and then D should be 70, 60, 50, 40. So let's see what happens when we do that. I'm going to put a sleep timer here just so we can have some time to actually see this output. So now I'm going to look at the output when I start it up. So let's give it a second here, and there we go. Align check. We see A, B, C look correct, but D is 70, 60, 50, but it's missing the 40. So why would it not have copied that 40? So, well, that's because there's actually a missing item in here. In order to properly align the data structure by 32-bit sections, it actually pads the data structure with a kind of a hidden variable in there. And we really don't want it to do that, because sometimes we want data structures that are going to be fully loaded from a memory location. So let's show you how to actually get around this padding issue. So we can do so by packing the structure. So I'm putting packed here on the end, and I'll add the definition here in the comma.h, but essentially we're setting the attribute packed on this data structure. So if we do that, let's see what happens. So let me copy this. We'll go down here and say this one's unpacked and this one is packed. So let me just change a few things here. AC2, check 2, AC2. Okay, let's make that. And actually there's one other thing I missed too. We need to set this to AC2. AC2. Yeah, so for each of these we want to make sure we're reading from the right data structure. So yeah, let's go ahead and make this again. And now let's start it back up. And now we can see, bam, it's got an error. So the problem is that's with the data being unaligned, packed and unaligned like that, the ARM processor just doesn't support that without the MMU enabled. So in order to support that, let's work on enabling the MMU. Now if you follow Sergey's tutorial, which I have mentioned in previous videos, he has this lesson 6 where he covers pretty well in detail how virtual memory management works, the translation process. It's got a nice diagram on how the different PGD, PUD, PMD tables are all set up. And he puts everything in this TBR0 register and the TBR1 TTBR1 registers. I'm going to do it a little bit different than the way he's done it because his is focused more on having separate kernel and user memory, but for me it's bare metal, and my project so far isn't really focused on having a user environment. It's more everything running in the kernel. Also, his only really supports Raspberry Pi 3, doesn't support 4 the way he does it. But actually, there's another good repository by someone named Rhythm16. And he's on the Discord channel, and he's helped me kind of get this working for the Raspberry Pi 4. And let's see if you look. This is the person here, Rhythm16. Looks like he's from Taiwan. And he's got this project here, RPi 4 bare metal. It's very much based on Sergey's tutorial, so his is also focused on having a user level and kernel level memory, and a lot more complicated. I'm going to do a much kind of simpler approach, rather than being able to switch between user and kernel mode and having two different registers to manage all the memory. So I'm going to use something called identity mapping, where it's a one-to-one mapping. So first I'm going to add in the make file. We're just going to have a flag so we can enable and disable this. Call it init MMU. So let's see, -d init MMU equals that value. So now in the kernel I'll just put some information here showing that it's initialized the MMU if it's set to 1, so that we know when it starts up if it's enabled. Initialized MMU. Of course, that's not all there is to it, but so let's take this and go into our boot.s. So in boot.s, first under this master section, let me just add this in here, and we have some extra registers that we need to set. So in the case of initializing the MMU, before we get into EL1, we need to first, we're going to load this CPACR EL1 value into X0, and we're going to write that into the CPACR EL1 register. Now another value we need to load in is the TCR EL1 register value. Load that into the register, and then the MAIR register. And actually Sergey covers that in pretty much well detail, what that register is and the purpose for it and all that. So I'd suggest reading that if you want to know more about some of these things. So I need to also include this MMU.H, and I'm going to just add it up here. Let's create a new MMU.H. This has several values. I'm just going to copy over. It's straight from Sergey's tutorial. So first we'll start with the pragma once at the top, and I'm just going to paste all this in, and it'll be in GitHub, so you'll be able to just see it from there. Okay. So that should have all those values needed. So let's go back to boot.s. So now down in the EL1 entry section, first I'm going to take this stack pointer and move it up. And so what we want to do after we do that mem0 of the BSS begin, let me again copy this over. So we only want to do this in case we are initializing the MMU. So we're just going to call this, we'll call it init MMU. That's the name of the function where we're going to put all this initialization in. Now in Sergey and Rhythm 16, they both do this all in assembly. I'm going to kind of do it in C, so it's a little easier to read for me. So next we need to load the address of the ID PGD table, and this is something we're actually adding to our linker. So that's the linker.ld file. So down here at the end, first I'm adding an align section. So now this is the section where we are going to store this identity table. And let's say .data.idpgd. So this is where the data for it's going to go, and the size of it is going to be 6 times 1 shifted over by 12, and that's, you'll see later, it's related to the number of sections that we have in here. So let's close that out. So we need to load that address because that's where we're going to be writing all this data. So we're loading the address into X0 so that we can use MSR to write that into TTBR0. So this is it's the register that will control the page translation when the MMU looks up memory addresses. So now let's grab the SCTLR EL1 value. I'm going to put it into X0. And then we're going to, into X1, we're going to put the SCTLR MMU enable flag. And now I'm going to OR those together and write it back to the SCTLR EL1 register. So that will essentially enable the MMU. So before we do that, we have to actually, so then it'll, jump down to the kernel. And before we do that, we need to actually implement this init MMU function. It's going to be pretty complicated. There's a lot of good details in Sergey's tutorial on what all these different things mean, but for now I'm just going to kind of trudge through it with you. So let's start off by adding a few headers to this. We'll add the, let's see, the peripherals base, we want that. The mm.h and our MMU.h. Probably should add printf in case we want to print out any stuff. This is actually before the printing is available, but we might use it later. So now let's start by, I'm going to paste in a bunch of defines, and most of these come from Sergey's tutorial and from Rhythm 16 has made some updates so that they'll work on Raspberry Pi 4. So I'm not going to go into them all in detail, but you'll see this ID map pages is 6, and the table size is 6 times page size, which uses that shift. That's where that value comes in from the LD file. Okay, so we'll start by creating a table. So we're going to have a function to create a table entry. And it's going to start with the table location, and then we're going to have the next table location, the virtual address, a value for shifting in, and the flags. So to start with, we're going to get our table index by taking the virtual address, shifting it over by that shift value. and we need to AND it with, let's see, entries per table -1. That'll get rid of all the other stuff that we don't need for the index value. So now we will get the descriptor. And the descriptor we get from the next table ORed with the flags. Okay, now we need to write all this data to, let's take cast the table plus the table index shifted over to the left by 3. That's the location where we're going to write the descriptor. So hopefully that makes sense. Putting the descriptor in the value of the location in memory here. That table plus the table index. So now we need a function to create a block mapping. And that's going to use the PMD table location. It's going to take in the virtual address start, the virtual address end, and then the physical address we're mapping to. So let's start by vstart. We need to shift it to the right by section shift. And now we need to AND it with entries per table -1. And now the vEnd, we need to essentially do the same with that, but we need to subtract 1 from it after shifting. And the same thing here. So now we're going to take our physical address, shift it over to the right by section shift, and then shift it back. That gets rid of some of the low bits. And now we'll go into a do while loop. So essentially for each of these addresses that we want to map, first I'm going to take the physical address. Now if the physical address is greater than or equal to the device start location, we want to use different flags. Device start I haven't defined yet. Let's see. So we'll put that in the base.h. So for rpi, it's going to be 3b4000, and for rpi4, fc followed by 6 zeros. So that's going to be where we need to change properties. Let me add a default value just to appease my IDE here. Or editor. It's not really an IDE. There we go. Okay. So now, so if PA is past the device location, then we're going to OR it with, let's see, TD device block flags. So otherwise, we're going to OR it with TD kernel block flags. And now we need to write this value, kind of similar how we did before. We're going to cast the PMD to V, adding with vstart shifted over by 3. And PA we're going to add section shift or section size and vstart ++, and we're going to do this all while vstart is less than or equal to end. And it looks like I spelled something wrong here. This should be PMD. So essentially we're looping through each of these locations and mapping the virtual to the physical. But in our case, the virtual and physical are the same address since we're doing an identity mapping. So now let's call these functions in our init MMU function. So to start off with, we actually need to get the address of this idpgd. So I'm going to call a function called idpgd adder, which we actually need to define and implement So U64 ID PGD adder. And I'm going to put that function in our boot.s. I'll just put it down here at the bottom. So we'll do global ID PGD adder and ID PGD adder. We'll just use ADRP into X0 ID PGD and return. So that'll give us the location of that block of memory, because that's where we need to start writing the data for our mapping tables. So first I want to clear that out. I'll use mem0 ID PGD, and the size is going to be the ID map table size. Okay, now when I get our map base is 0, because I'm going to be starting at 0. And the table is ID PGD, and the next table is ID PGD plus the section size, or page size, sorry. So now let's call create table entry, where we pass table, next table, and then our map base. The shift value for this is going to be PGD shift, because it's the PGD table. And the flags are TD kernel table flags. So now that we've created our PGD table entry, now I need to increment this table and the next table. Okay, so now we'll create another variable here for the block table. It's going to equal the table, the current table. Now on a for loop, we need to do 0 to 4. Alright, so now we're going to create table entry. This is going to be essentially the same as that other one, except instead of PGD shift, it's going to be PUD shift. So yeah, PUD shift instead of PGD shift. So we're creating 4 of those tables and 4 block mappings for them. So next table plus equals page shift, map base plus equals the PUD entry map size, and block table plus equals page size. And now we can say create, or actually do our offset. Our offset is the block size times I. So the block size is this value here. So it starts at 0. And so now when we do create block map, we're mapping the block at that block table from offset to offset plus block size, and then the physical address starting at offset. So we're mapping, this is our identity, we're mapping virtual to physical is the same value. Normally you won't do this if you're doing an operating system or something like that. There's other ways of doing this that are much better, but this is the simple approach that I just need to get the MMU working. So let's try to build it, and I'm running into some issue. I think I missed a couple of things. I need to add something to our sysregs. So let's go up to our sysregs, and I'm pasting in some values. These I took from Rhythm 16. He has a bunch of extra fields here, and I'm not going to go too into detail on them. He put some good comments on there as well. Again, check his GitHub page for some more details. So let me save that, and I think that's all. Let me make clean and make again. And okay, there we go. So now I'll jump over here and restart it. Give it a second to boot up. And so now we have our unpacked and our packed section. So if you notice in our packed section, D is correct. It's got 70, 60, 50, 40. So it actually packed the structure correctly, so all the data is in the right place. So yeah, you see the A is 10, B is 20, C is 30, D is 70, 60, 50, and 40. So it all looks good. And that's not possible without initializing the MMU. So let's go back, and I'm going to make clean and set the flag to 0. So I can say init MMU equals 0, make. Okay, let me copy this over again. And start it up. And sometimes I need to unplug my cord and plug it back in for this startup to work. Let me do that. And I'll start it up. And here we go. So again, this is no MMU, and we get the error because there's no MMU. So we can say that this works properly when we enable the MMU, and without the MMU we get the unalignment error. So that's most of what I really wanted to go over in this video, but since we're dealing with memory, I'm going to go ahead and add some allocation as well. It's not really allocation, it's more like reserving pages, but let's start with a simple memory map which has paging, pages, number of pages, and this I'm taking straight from a Sergeys tutorial as well, but I'm kind of modifying it some. So his is let me find the source here. His is more for fetching a page at a time and then doing something with it. Let's see, it's down here in mm.c, I think. Yeah, so you'll see some code copy in here, but this is where he's allocating pages. Yeah, I shouldn't use the word allocate, but you know what I mean. So he's doing one page at a time, but I find that when I need memory, I generally need it in larger chunks at the kernel level. So I'm going to actually add some values here. I'm going to set the high memory location to 1 gigabyte, so everything between low memory and high memory is going to be the data that we're going to be able to allocate with our page by page allocator. So let me save that and go back to mem.c. So each value of this table, if it's 0, that means it's unallocated, and if it's 1, that means, or non-zero, that means it's allocated. So what I'm going to do is get free pages. So you give a number of pages that you want, and they're going to have to be contiguous, of course. So let's say a start index of 0 and a count of 0 to start off with. So now I'm going to loop through each of the available pages. Paging pages. So if that page at index I is 0, that means that it's available. So it's not yet allocated. So what I'm going to do is say, let's see, if not count, that means I don't have any other pages yet. I'm going to set the start index to that current value. Now I'm going to say count plus plus. And if count equals the number of pages, that means that I was able to get all pages together. So now I'm just going to memmap start index equals count. So I know how many pages have been allocated after this. So I'm setting that value to count. And now for each value after that I've allocated, so for 1 to count, I'm going to set their value to 1. Because really I just need some value in there. And let's see, so now to get the pointer, I'm going to cast void pointer, low memory, plus the start index times the page size. So that will give me the location in memory to use for a pointer. And I'm just going to add some print details just so I can kind of debug if problems happen with this. Add address %x. So count, start index, and p. Then I'm just going to return p. And now, so if the mem map is not 0, that means this one's already allocated. So what I need to do is set count to 0 because I want these all to be in a row, contiguous memory that I can write to. Alright, so let's just double check. Yeah, everything looks right. So I'm going to take this and put it in our, should I put it in mm.h? No. I think there's a mem.h. Yeah, mem.h. I'm going to put it down here. And so now let's add a helper function because we don't always want to have to calculate the number of pages we need. Let's add a function called allocate memory where we pass in the number of bytes that we need. So in order to get the number of pages we need, we just take bytes, divide it by page size. And now if bytes % page size, that means there's some leftovers, then we need to add another page to it. So 4097, it would, instead of 1 page, it would be 2 pages. So then we just return get free pages. And now we want to be able to free that memory back too. So let's say free memory, give it the base address. And now let's say we need to get the page number from that address. So in order to get that, first we cast to U64, subtract low memory, and then divide that all by page size, which is essentially what we did down here, but the reverse of it. So we're just kind of pulling that pointer apart and grabbing the data we need from it. So now the number of pages that were allocated in it is going to be from that memmap value that I'd set. Remember we set count there. So then we can just say, let's print some debug information here. Free memory. See at address x page num %d and pages %d. So base, page num, and page. So now in order to do the actual freeing, all we essentially do is just set the value in memmap for each of the pages that we had allocated to 0. So page num plus I equals 0. Okay. So now let's go to our kernel.c and just put some data in here that we can play around with our allocator. So void p1 equals get free pages. We'll get 10 pages. Let's just copy this. We'll do p2 and p3. So we get 10 pages, get 4 pages, and this time we'll use the allocator. So allocate memory. We want to get 20 pages of memory, so we'll do 20 times 4096. And let's add 1. So that should be 21 pages instead because we have 1 over the amount we need. Okay, so and then we can free these pointers when we're done. So free memory, we'll do P2, maybe do them in different order. Let's copy that and paste. So we'll do free memory P1, free memory P3. Or do we want to do them in the same order just to make it easier to read? Yeah, let's just do them in the same order just so it's easier to read the debugging statements. So I'll just cut this and paste it in front of it. So now we should be able to build it and see the output of the debug. So let's make. Okay, and we'll take it out and we'll start it up. Give it a second to start here. And now you'll see it printed out our get free pages. Return 10 pages at address 0, or at 0 at address 400,000. And then 4 pages at A00 and 21 pages. That looks all correct. Freeing the memory, page num 0 at pages 10, and then 14. So all that looks correct. So yeah, I think everything looks pretty good. So you should be able to play around with that some, play around with writing to those memory locations, should be safe. So I think that's really it that I wanted to cover for this video. Just wanted to kind of get back on track with the Raspberry Pi Bare Metal series. So I think in the next one I want to start looking at how to read data from the SD card. That's probably what I'll do in the next video, because now that the unaligned stuff is all out of the way, I'm able to do more things like that. So I hope you enjoyed this video. If you did, like, comment, subscribe, and we have a Discord channel, so Discord server. So if you want to join that, I'll have that in the description as well. So thanks for watching.